Let me thank you, the organizers, as the usual kind of statements one makes at the beginning of these conferences. As Jake put it politely, the reason I've been asked to open it is just because I'm the oldest here in the audience and among participants. And it's rather impressive, I mean, the kind of progress that researchers on these topics like quantum thermodynamics and quantum systems and quantum technology has been going on here in Malta. Okay, so I'm particularly pleased to be here and to help and contribute in a way or another. This first talk, which is an opening talk, will be rather pop, if you like. It will be rather light, and we'll try to sort of put in perspective what are the links between quantum computation and quantum thermodynamics, and we'll see that the two things somehow evolved in parallel from the very beginning of the, both conceptually and historically. There are strong links between thermodynamics, statistical mechanics, quantum computation, and microscopic model of computation. Okay. How do I scroll the slides? Okay, here it is. Typically, whenever you go to a physics seminar, people like to point out how much technology comes from research going on in foundations. A typical example is Faraday on the top left. He was doing his early experiment of electromagnetic induction. And when somebody asked him, I mean, what is it useful for, I don't have any clue, but for sure, if there is an application for what I'm doing, there will be a tax on it. Now we pay electricity bills, of course. So the early research, on the one hand, of Maxwell on electromagnetic waves, on Fermi, on nuclear physics, on towns, and on superconductivity by Bardeen, Cooper, Schiffer, turned out to have, I mean, probably even outside, not just superconductivity, also the transistor technology. He's not Bardeen, Cooper, Schiffer, he's Bardeen, Shockley, and they got the Nobel Prize for the invention of the transistor. I mean, they started their research as basic research, and then these had strong impact on technologies. But in the case of computation and thermodynamics, things have gone somehow the other way around. Come on. Thermodynamics is a typical example in which you go to foundations starting from technological application. People like Carnot and Lord Kelvin, Joule and Clausius were interested in how you build engines. I mean, all this research went on during the period of Industrial Revolution. And so they were interested in practical application. I mean, what is the optimal working of an engine? But the reason there was this research going on was for very practical reasons. Of course, they asked fundamental questions. So what is the ultimate limit? What is the best you can do? But everything started from very practical reason. I like a lot this picture because, I mean, in particular, Lord Kelvin and Joule can sport a lovely hipster beard, which is probably Klaus is a bit more stirred. The interesting point is that they, on the one hand, introduced the three key quantities, the three key physical quantities which you study all through your thermodynamics course or statistical mechanics course, which is temperature, energy, and entropy. And particularly we see the entropy, which was first introduced in formal terms in the way we know it now by Clausius, is basically the trait d'union, is the link between information theory and quantum computation in general, and quantum in particular, and thermodynamics. And another, I'd like to point out that Carnot, and basically the discovery of the second law of thermodynamics, historically dates before the first principle of thermodynamics. I mean, Carnot made his analysis of the maximum efficiency of thermal engines without even knowing what is internal energy or without having a clear definition of what heat is. And still, I mean, the interesting point is that they carried on their analysis in terms of, if you like, abstract but practical device. So studying the functioning of a specific device and asking yourself what is the best you can do and showing that this is the best you can do with any kind of device, not just his engines, is an interesting way, is a paradigmatic way in which you analyze the best you can do with a physical system, and the best, I mean, a way in which you analyze in the most general term, starting from something which looks very particular, it looks a very specific engine, and to reach general conclusion. We'll come to temperature, energy, and entropy again in a moment, but just let's keep in mind that the way in which the early father of thermodynamics thought was in terms of a specific model, and then from there they generalized everything. Another, is it? Okay. Another field in which you go from very practical applications to foundations, I mean, to fundamental question, is computer science and information theory. Information theory and computer science, I mean, evolved somehow in parallel. Information theory is linked with the name of Claude Shannon, and computer science, the father can undoubtedly be named as Turing, ask themselves fundamental questions, like, I mean, what is information? Very much the same way in which people working in thermodynamics were asking themselves, what is energy? I mean, how can you exchange energy? And then they ask questions, very general terms, like, can you transmit information error-free in the presence of noise? There's a misspelling, I've read noise twice. On the other hand, again, Turing asked himself question, I mean, can you describe in abstract and general terms any computing device? Very much the same kind of things that Carnot asked himself. Can you describe any engine starting from a specific model? And from this, he asked questions like, which functions can be computed? I mean, how complex is a problem? Can you solve any problem, or there are problems which cannot be solved? And this, I mean, he got all these results by, again, introducing an abstract model, which is the Turing machine, which I assume all of you know. I mean, the Turing machine can be thought like the Platonic ideal kind of archetypical computing device in which you have a headset with a set of internal states, a long tape, and on a tape you have a set of symbols, typically 0s and 1, and on the headset you have your a set of internal states, which there's a starting state and a halting state. The head goes onto the tape, reads what is on the tape, changes the state, the symbol which is on the tape, it changes its internal state and goes to the left and to the right. I mean, you all know basically how the a Turing machine works. And very much the same way in which Carnot showed that any engine, any thermal engine can be described in terms of his engine. I mean, the efficiency of any thermal device can be analyzed in terms of just to adiabatic and to isothermal. Turing showed that any kind of computation can be analyzed in terms of his machine. So you think of a mechanical device which looks very particular, but which actually allows you to answer the fundamental question, and in particular allows you to reach answer to what are the limits of what you can do. For instance, in particular, the Turing machine allowed to introduce the concept of complexity of a problem. Okay, you think of an algorithm like a series of operations, in particular as a sequence of states of your headsets and your tape, and this allows you to quantify the amount of resources you need to solve the problem. In terms of the time it takes to your machine to solve a problem as a function of the input. Very much in the same way in which you, in a Carnot cycle, you ask yourself, how much work can I get out, provided I put in a certain amount of heat, exchange a certain amount of heat from a hot and cold reservoir. So that conceptually, I mean, if you look at these two problems, which are quite distant from one to the other, they have strong analogies in the way in which the father somehow thought. So they start from a particular specific device and they reach general consequences. Okay, but the analogies and the links between information theory and thermodynamics, I mean, is not just in the fact that the father of the two fields thought in the same way about how to solve problems, how to provide answer, but the clear historical moment in which the two things, information theory in particular, not that much computation, we'll come to computation in a moment, but information theory and thermodynamics, I mean, show the fact to be strongly linked with each other, was again with Maxwell. Okay, at the time of Maxwell, you start to realize that thermodynamics has a statistical nature. It's linked to the fact that there are that matter is made of microscopic particles, and these are the statistical properties of a large number of particles that which are the origin of the laws of thermodynamics. And as you all know, I mean, because I mean most of you are advanced students, I mean Maxwell asked himself, what about if I got a small demon which can acquire information about the state of individual molecule? And this, if this demon can use the information gained on the specific speed of individual molecule, and by opening and closing a trapdoor, it can create a temperature difference between the two halves of a vessel which is filled with gas. And then you can use this temperature difference to operate a thermal engine, therefore violating the second principle of thermodynamics. And so he basically he linked the second principle of thermodynamics with statistical, with the paradoxical consequences of the which may arise from the statistical nature of thermodynamic laws. And as you all know, I mean, the next step was again the study of an idealized engine, which is the Zeeland engine, in which is basically a Carnot engine with just a single, operated by a single molecule, and going on this path, basically we arrive to a crucial point in this story, which is Landauer, I mean, who with his slogan "Information is physical," made it clear that the information is itself a resource, is something you can quantify very much the same way you can quantify heat, and you can quantify heat or energy. In particular, I mean, by studying, making use of the Landauer principle, Charlie Bennett was able to show that the second principle of thermodynamics is not violated by Maxwell demon, because you basically, if you want to acquire information, you want to do it by a process which is cyclical, which means at the end you register the tape on which you register your information is back to the original blank state. You must erase this information, and erasing information at finite temperature implies that you must dump energy into your reservoir. So again, this is a crucial moment in which information theory and thermodynamics get strongly linked with each other, and information theory provides an answer to an opening paradox of thermodynamics. But at the same time, people started to look, I mean, starting from the fact that the processing of information and not only the erasing, but any processing of information is basically a physical process. People started to look at a way in which you can implement computational process. So we are now moving from information theory to computer science. Whether you can implement you can implement gates which do not erase information, which therefore can operate with zero thermodynamic cost. So very much the same way in which Carnot asked himself the question, what is the minimum, what is the maximum efficiency of our Carnot engines? I mean, people like Bennett and Toffoli and Fredkin, and following the pioneering work of Landauer, asked themselves the question, what is the thermodynamic cost of computation? In the case of classical computation, but they open the way in which, they open the perspective of looking at computational process not just simply as an abstract process, very much the way in which Turing did it, but in terms of a sequence of physical operation. So the same Turing machine, if you like, is not just an abstract device, but it's a device which operates on a particular physical system. And if you don't use the Turing machine paradigm of computation, but you describe computation in terms of gate, again, you should ask yourself, is it possible to devise gates which operate with no logical loss, which means that you don't erase data, and therefore could in principle operate zero thermodynamic cost. And the ballistic computer, which was a very idealized model of computation, was the early attempt, which now looks a bit naive, but is interesting anyway conceptually, in which you can perform computation, but just following the path of individual billiard ball, and which are reflected by mirrors. Of course, anybody studying chaotic dynamics is perfectly aware that this is not going to work anyway, because, I mean, if you don't have perfect control of the angle and the tilting of at each reflection and the position of the mirror, and if these billiard ball are microscopic, I mean, Brownian motion and not perfect control of initial condition would lead to chaotic behavior. But still, it was an interesting perspective, because are the very same people who started looking at physical implementation of reversible computation that started the field of quantum computation, we'll see shortly. And again, as I said, people started looking at Turing machine, not just gates, but also Turing machine as specific devices or specific computing machine which is based on some particular hardware. And at that time, being a hardware thermodynamic interest, there was a lot of research going on in terms of molecular computer or molecular Turing machines or enzymatic Turing machines. Here on the left-hand side of this slide, you see an example of possible implementation of a Turing machine with a headset, which is this enzyme which moves along a strand of biomolecules and modifies the chemical element which sticks to each point of this strand according to a set of rules which are mapped into the structure itself of the enzyme. This is an interesting kind of, and by the way, enzymatic Turing machines or DNA Turing machines have been really implemented by biologists and computer scientists, and particularly by Adelman, which is the Adelman of the RSA crypto system. The interesting point of these engines, which are biological engines, is that you can study the thermodynamics of these devices. Don't forget that Clausius was something in between a mathematician and a chemist. Is interesting for entropy, came from the chemist viewpoint. And don't forget that Charlie Bennett is actually a chemist. I mean, although everybody thinks he's a physicist, he's probably hiding his true original background as a chemist. And therefore, you can ask yourself, what is the power which is needed? What is the difference in chemical potential? How much chemical elements you need to put into your solution to drive this computation in one way or another. And depending on the concentration and the temperature, you can drive your computation backward and forward. And this started basically the study of what are known as Brownian computing machine, which is, again, a typical example in which you link thermodynamics and computation in terms of resources, efficiency, and cost of a computation. And at the same time, this allows you to analyze fundamental limits of what you can do. Okay, now let's go to the quantum scenario. I mean, what is the role of quantum mechanics? Again, quantum mechanics and thermodynamics, in particular statistical mechanics, are strongly linked historically. On the one hand, Einstein pointed out that, I mean, although thermodynamics can be thought, I mean, especially when you're a student, you think that thermodynamics, you know, is a sort of dirty kind of physics. You make some assumptions, you're never sure what's going on, you make some postulates, but actually this is not a weakness, this is a strong point of thermodynamics in the sense that you start from very, very few basic assumptions and you come from and you reach very general conclusions which do not depend on the detail of the system you are working. And these honest, simple expectation that you have from the very beginning turns out to make thermodynamics as a very solid field, in the sense that classical mechanics did not survive. I mean, it was surpassed by relativistic mechanics and by quantum mechanics, and still thermodynamics is valid both in the thermodynamic regime and it survived the quantum revolution. And actually, one must say that it was the attempt to answer to a thermodynamic problem, which is the black body radiation. We try to explain what the black body radiation is, that started all this Planck affair, this Planck stuff. So, I mean, again, statistical mechanics and thermodynamics are at the very core, the very origin of the birth of quantum mechanics, if you like. And then you need quantum mechanics to explain the thermodynamic properties of matter. So if you want to apply statistical mechanic techniques to explain thermodynamic properties of a macroscopic body, you must remember that macroscopic bodies are actually quantum on a microscopic level. And this, on the one hand, again, allows you to explain the behavior of solids and the black body radiation. But on the other hand, if you use statistical mechanics and to systems which are intrinsically quantum, you predict phenomena like the Bose-Einstein condensation, which they've been observed in nature. And also, I mean, from purely thermodynamic reasoning, you can predict the Einstein, you can even evaluate the Einstein A and B coefficients. I mean, basically, Einstein, the only thing he did was to apply thermodynamics to predict what would be the transition rate of atoms and lasers. Of atomic transitions in the presence of external radiation. However, now, both in the case of thermodynamics and of computation, you ask yourself, okay, fine, but what happens? Most of what I've said before, I mean, in my previous slide on the link between thermodynamics and quantum mechanics is, if you like, sort of mean field, macroscopic behavior of objects. But what happens if I'm interested in the, on the one hand, in computing devices which operate at the microscopic scale, and on the other, on thermodynamics engines, which again operates at the macroscopic scale. And then, of course, you begin to ask yourself whether you can use resources like coherence and entanglement as the resources that you can use to very much the same way in which you use heat and work and entropy as resources for engines. And this has led, on the one hand, first on the idea of a quantum Turing machine. Okay, let's think of a Brownian Brownian Turing machine. A Brownian Turing machine is like a Turing machine in which your headset moves on your tape according to some transition rule. Okay, and then you can say, okay, rather than having probabilities and you move along a specific well-defined path, but probabilistically forward and backward, you can go one step further and ask yourself, what happens if I if I have a Turing machine which performs computation probabilistically? So it gives you an answer to your problem, but you're not sure whether the answer is correct or not. And suppose that the answer could be wrong, but the machine gives the answer very rapidly. And then you can check whether the answer is correct, I mean, with a polynomial algorithm, which means you can check whether the result is correct or not in a very short time. You can solve in a short time a problem which on a standard Turing machine, which is a purely deterministic Turing machine, would take probably a very long time. So the next step is, okay, rather than having a probabilistic Turing machine in which you follow a possible computational path with a given probability, the answer may be wrong, but you can check it fast. You can think the following way: what about a Turing machine in which you can follow different paths at the same time, because basically you, using Feynman principle, your computer follows different paths all at the same time, and they can interfere, and you substitute probabilities with probability amplitude. So, I mean, is coherent interference between computational pattern something useful? And this was the birth of the first quantum computer by David Deutsch. But then again, if you don't want to analyze your quantum computer in terms of Turing machine, you can do it in terms of quantum gates. And then again, quantum gates, well, you all know it, if even at the junior level of this audience, you all know what a qubit is. So you can operate of qubit, creating coherent superposition of internal states. And again, you can view your computer like a giant interferometer in which your mirrors and create superposition, and then these various computational paths interfere. So it's a different kind of architecture with respect to the Turing machine one, but conceptually the same thing. You think of your computing device as a giant interferometer. Similar kind of questions have emerged a few years later in the thermodynamic area, and this somehow give the birth of what we now call quantum thermodynamics. So far I've been discussing what are the links between quantum physics and thermodynamics, but now the next step is to ask, again, very much the same way you've been using concepts like coherence and entanglement for quantum computation. Can you use coherence as an ingredient, as a resource to operate quantum engines? And perhaps the first example of this way of thinking, well, it's not the first, well, I'll come to this in a moment, is the so-called phasonium, which was introduced was analyzed by Marlan Scully, and the idea is to have your working fluid is a photon gas, but then you pump your photon gas with a set of atoms, which can have in a lambda, which have an energy structure, a typical lambda energy level structure, and you create coherence between the two ground states, as you see here on the right topmost figure. And according to the phase of the coherent superposition of these B and C states, which are the two ground states of your atom, you have an interference mechanism which allows you to control the temperature at which you thermalize your photon gas within the cavity. And he was interested in how can you use this to to operate a Carnot engine which is more efficient, if you like, with respect to the standard Carnot engine operating with a normal fluid. The interesting point of this device is, again, it is possibly the first instance, at least as far as I know, in which you look at coherent effect, look at coherence like a resource which you can, in a way, use to operate a quantum engine. It must be said that the analysis of a quantum device from the viewpoint of a quantum engine dates well earlier than this paper by Scully, which has been published in 2003. And it dates to the very early stage in which people were doing research on laser. So there's a paper by Dubois and I forgot the name of the other authors, Svozil, okay, in which they analyze, I forgot to put it on a slide, but this is extremely interesting. They analyze the laser like a continuous thermodynamic engine, in which you provide energy at one temperature and you extract energy and you transform it into a coherent signal and you dump energy at a lower temperature reservoir. So with just using Boltzmann factor, you can immediately work out the efficiency of this continuous engine, which is a quantum engine, quantum thermodynamic engines, in which you incoherently pump two energy levels, which means it is like exchanging energy with a high temperature reservoir, and then you dump some photon between the two other levels at a lower temperature, and in between you emit coherent photons which make up the laser. And you can evaluate how efficient this process is, and it turns out to be very much the same efficiency you would expect by a Carnot engine. So it's interesting you analyze the working of a quantum device in terms of a quantum thermodynamic engine. This paper by Scully is one step further, and you explicitly begin to look at how an ingredient like coherence can be used to improve the efficiency of a quantum engine. But then, I mean, time was ready for the birth of quantum thermodynamics the way we know it now, in which you make an analysis of resources which are coherence, which are entanglement, as something which can use to operate quantum devices at a microscopic scale, like the ion trap Otto engine, which has been which has been physically implemented in Austria by Ferdinand Schmidt-Kahle. And for this kind of engine, you can show that you can use coherence, or you can engineer your reservoir into non-classical states, and this is an additional resource that you can use to improve the efficiency of the engine in appropriate regime. Something which must be pointed out is that we are not stating, I mean, quantum thermodynamics so far has not made any claim the fact the second principle of thermodynamics is violated. It simply added new resources as something you can play with to optimize, I mean, the efficiency of your engine. So rather than using simply energy, and if you want to take into account the amount of coherence and whether it can be used to improve the efficiency of a device, people have introduced the concept of ergotropy, which somehow quantify the maximum amount of work you can extract from the cyclic evolution of a quantum device. On the other hand, especially in recent years, people are going beyond the standard paradigm of computations and quantum algorithms in terms of either Turing machines or more specifically in terms of quantum gates. And typical example are sort of neuromorphic kind of computations, like a form of computation which draw conceptually from the architecture based on neural networks. Okay, so you can think of new way of computing in terms of quantum neural networks. In particular, you can have situations in which a large system, which is a reservoir, is not, if you like, noise is not a problem, but is a resource itself for your computation. Very much the same way in which by engineering the environment you can improve the performance of a computing device. I've been very fast, but I've basically reached the end of my talk, and just sum up what I've said and what I think are the perspective and things we will look at. I expect the research to look at in the next few years. And so far, what we have seen is that entropy is a crucial role in both thermodynamics and statistical mechanics and information theory. And indeed, you can show that the very same entropy, which call it Shannon entropy, can be used to derive all your ensemble theory by a maximum entropy principle with a constraint. So you can use you can derive your macrocanonical, canonical, grand canonical ensemble, but just postulating, rather than introducing a Boltzmann entropy or introducing a Gibbs entropy or whatever, you just start with your standard Shannon entropy, and you maximize it according to the constraint you have, and you can derive any ensemble theory. But then you ask yourself, okay, the ensemble theory, very much the same way as the Shannon theorem, on the one hand introduces the concept of typicality, typical strings that you transmit along a channel and which are used to transmit safely information even in the presence of noise, or can allow you to compress information. And on the other hand, typical states are the one which allows you to derive a meaningful thermodynamic properties of a system in the macroscopic limits for the canonical ensemble, because you know in advance that although the system exchange energy with your environment, it will stay in a manifold of states in a region of your phase space which is the typical one. So one open question is, that we have not mentioned so far, I mean how you derive the concept of temperature, and how can you derive the concept of typicality from a purely in a purely quantum setup? So I mean, how does thermalization emerge from a purely quantum description of your system, which may be pure? And one of the idea, there is still a lot of work to be carried on in this field, is to change the microcanonical assumption with the assumption of random states, okay, which are uniformly distributed according to a given measure. And if you take a part of your large Hilbert random state, you take part of it, you get something which looks very much like a thermal state, very much the same way in which you're going from a microcanonical ensemble, you go to canonical ensemble. There's still work going on this, but this was one of the first problems which have been addressed in what is, if you like, modern day quantum thermodynamics. And again, historically, people have been looking at how to go from microscopic ensemble of the behavior of a large number of systems. You take the ensemble average of the dynamics into the following the trajectory of individual subsystem. So if you go to macro to micro, you can get you go from the field of thermodynamics to the field of stochastic thermodynamics. And stochastic thermodynamics, as some other colleague will probably talk about during these this series of lecture, allows you to follow to ask yourself, I mean, how the thermodynamic properties of individual particle behave, and you can ask yourself what is the minimum, what is the guarantee efficiency of a macroscopic engine which operates with just at the macroscopic level, and what is the minimum guarantee efficiency, or you can derive the fluctuations relations, which are typically one of the cornerstones of stochastic thermodynamics. And all this then go from the classical regime, you can then map them to the quantum regime. And this is much of the work which has been going on in this field over the past few years. Going to from macroscopic classical system to macroscopic quantum system, on the one hand, you go from stochastic thermodynamics and classical, if you like, fluctuations relations, which link equilibrium, non-equilibrium fluctuations of your work, for instance, with the equilibrium property of your system. And you can do something, you can map them on the quantum, at the quantum level, and you can ask, I mean, what is the optimal efficiency on the one hand of macroscopic engines, and on the other hand of quantum algorithms which are based on macroscopic gates, and what are coherence and entanglement as the resources. So open questions, well, some of these questions are no longer open in the sense that people have been giving answers, but anyway is what people are doing research on, I mean, nowadays. How can you extend part of the results which have been obtained in terms of thermodynamic of computation from a standard being gate-based computation, although there is still, I mean, working going on. I mean, how can you extend this result to the case in which you are using neuromorphic paradigm of computation, for instance? I mean, what is the thermodynamic cost of quantum neural network computation done on these kind of devices? What is in general the energetic cost of computation? Now you have, no? There is very much, if you like, a strong debate on the policy of science, on what should be funded, what people should be looked at, what is interesting for what is of collective interest is the energetic cost of computation. Very much you're asking yourself, I mean, how you're paying your gas bill or your petrol bill. So basically, people are asking, I mean, okay, quantum computation is fine, but how much it costs from the energetic viewpoint? You know already that some artificial intelligence algorithms are very much energy consuming, or if you like, I mean, Bitcoin mining, if you like, is extremely energy consuming. So you must ask yourself, what is the energetic cost of some computational algorithms you are going to implement? So it's very much an open question of very much general public interest. Again, the quantum origin of temperature is not something which so far has been fully clarified. So there have been some attempts, successful in many respects, but mathematically rather sophisticated. I mean, not easy perhaps to follow in detail. What is the quantum origin of temperature? As I mentioned before, random states and typicality are something which appear to be linked with each other, but again, especially in the case of many body system, is something which needs to be further studied. And finally, quantum noise. I mean, we will start talking in next lecture about quantum noise, the effect of noise, I mean, has on the dynamics of the non-unitary dynamics of quantum system. But in general, people begin now to consider quantum noise not just as a nuisance, as something which prevents you from doing computation, but something which can be used as a resource. Again, what are known as quantum reservoir computing tends to think of large systems which are, if you like, intrinsically open, if you look at part of the subsystem, as a way in which you can do, you can implement new form, a new paradigm of computation. I think I'm done. It's high time for a coffee, probably. Okay, thank you.
We have like 9 or 5 minutes left. we have these fun boxes which we can throw around, so like ask questions. Does anyone have questions for Prof. Palma? Maybe, like, I'm gonna like fully commit to this.
Okay, this was it. Okay.
Thank you for the lecture. I have two questions. The first one is simple. What is typicality?
Okay. Just toss a coin, okay? And a coin can be either head or tail. And you toss a large number of coins. A typical sequence will be one in which, if the coin is unbiased, a typical sequence of coin toss will be the one which about half of your toss will be head and the other half will be tail, okay? So this is a typical sequence. And when you want to transmit information, the fact that you can transmit information safely, or the fact you can compress information from a data string, relies on the fact that not all strings are equally likely. Some strings are more likely, have some properties which makes them more likely than other. In other words, to put it more precisely, there is a subset of all possible sequence of signaling in the case in which you are transmitting bits or information, for instance, which are more typical than other. This is something which is used, for instance, in decryption, okay? In the spoken language, not all letters are equally likely. E is more likely than other. If you do, crypto crosswords, you put letters in numbers. What numbers is more frequent than other? Okay, so the frequency of a symbol, of each symbol of your alphabet, makes a specific specific sequence typical. In thermodynamics, this maps in the following properties. If you have a box filled with gas and you insert a sect which divides the box into two halves, the vessel into two halves, and you have a hole, basically half the molecule, if you divide it into equal parts, half the molecule will be on the right and half the molecule will be on the left. They can hop from one side to the other, but it's extremely unlikely that all the molecules will hop on the right and on the left. So this is, very crudely speaking, the concept of typicality. The thermodynamic properties of a system are determined by the typical set of states in the phase space. Okay. Now, if you go to suppose you're looking at a quantum system and you assume that the state of your system and the environment is overall a pure state. How can you, how does it come that if you look at a subsystem, this will have thermal properties? Okay, so you have a large system, which is system plus environment. You look at just your system, you trace out the environment, degrees of freedom. How is it possible that the statistical properties of your subsystem are so well described by the Gibbs ensemble? So which is a thermal state. And one possible explanation, people have been trying to explain this, saying, okay, the overall state, system plus environment, is a pure state, but it's random, uniformly distributed a priori on a given Hilbert space. And how do thermal properties emerge on your subsystem when you look at just parts of the system and you trace out the environment degrees of freedom?
Okay, and the next question, if you don't mind. Could you just perhaps explain in basic how could we apply a quantum computer in order to mine Bitcoin?
Sorry?
How could we apply quantum computer in order to mine Bitcoin?
In order to what? Sorry.
In order to mine Bitcoin.
I have no clue whatsoever. The answer is simple.
Time for one more question. I saw Dr. Apollaro raised his hand earlier. So, Leonard, can you pass it to him maybe?
Great.
Tony.
So, thank you for... I'm talking to a pillow. Okay, I generally do it as well. Good, okay. So, thank you, Massimo, for the comprehensive talk. Now, I have something between a comment and a question. So, I think at quantum mechanics, it's full of you cannot do that, you cannot do that. You cannot measure position and momentum at the same time, for instance. Then I think at the thermodynamics, in its also quantum version, and again, you cannot do a lot of things, like you cannot beat Carnot efficiency or some formulation of second and third law of thermodynamics. Then I think at quantum computation, and there's still, again, a lot of things that you cannot do. You cannot clone a qubit, or you cannot clone an unknown quantum state. So my question is, those no-go theorems, are they connected? Can they be derived one from the other? So probably something about the no qubit, no cloning theorem. Is it related to if one could clone, then second law of thermodynamics would be violated? And then the other, going a bit higher, say, has it something to do with computational complexity? In the sense that, is it possible that there are problems that a quantum computer cannot solve, not because of logical or problems, but because there are no-go theorems coming from other fields of which it is connected.
Okay.
So, thank you.
There are lots of things you cannot do with the quantum computers, but there are a lot of things that you can do with the quantum computer you cannot do with a classical one, so on the one hand. Let's start with the second question. If you read the early papers on quantum computation and quantum algorithm, the typical statement is that if you look at the early version, the early algorithms, typically you get, quantum phase estimation, or you get Shor algorithm, or Simon algorithm, things like this. And they're all based on Fourier transform, some sort of Fourier transform. And the reason they are all based on some sort of Fourier transform is, again, the fact that it's true that the quantum computer is a coherent superposition of all its internal state. But when you measure the output register, you collapse its state. So you cannot solve problems in which, for instance, you ask what is the value of a given function for each possible input. If the question is this, you must run your quantum computer, if you have n possible inputs, and you're interested in the individual output of each possible input, the output of the function for each possible input, you must simply evaluate you must run the computer very much the same way you run a classical computer. Quantum computers, at least the early version of quantum algorithms, are efficient whenever you are interested in global properties of your function, some sort of periodicity. So basically, all the earliest algorithms are basically some sort of Fourier transform, which of course are something which is very natural in the quantum scenario, because changing base is nothing like that. Is basically taking a Fourier transform. Fourier transform is one of the first things that you learn in your third year quantum mechanics course. But now, so much of the interest so far has been towards what is the optimal quantum algorithm. Have we reached the quantum supremacy? Are there problems which can be solved only on a quantum computer, which cannot be solved in any reasonable time on a classical computer? Which is, on the one hand, a legitimate fundamental question, but on the other hand is also a legitimate selling slogan, in the way you've built a quantum computer which is of a reasonable size, like Google or IBM or whatever, and you want to show that although it's not, you cannot still implement fault-tolerant quantum computation, your computer is not yet quantum error-free, because again, you cannot implement fault-tolerant quantum computation. It's too small, but still you can solve problems more efficiently that you can do with any other classical computer. And in my viewpoint, is at this stage is nothing more than just a selling slogan. On the other hand, it's interesting the way computer scientists begin to think of quantum computation is different from the way in which physicists think of computing process in terms of a quantum computer. They are not interested in what is optimal. and if it is the best algorithm, or if there is no classical computer which can solve it. But can you just mix in quantum routine with the classical algorithm, something which is conceptually dirty, if you like, but you just mix different ingredients, do something which is even slightly better, of a certain percentage better than just using a purely classical computer. And on the other hand, there is another way of thought that say, okay, a classical computer is not a quantum computer, but still you can organize your classical algorithm, your classical routines, based on what you have learned from the quantum case. So these are called quantum-inspired algorithm. And I'll give you an example. I met a couple of months ago the technical chief officer of our national electric company, okay? And they wanted to optimize basically workers' shift. Okay, so what optimize, I mean, who was supposed to work where, when, from when to what, in which place, and it is, of course, a complex optimization problem. I think there is something like 25,000 input variables, and they have to optimize in a very complex landscape. And they tried with a quantum annealer. Of course, they did not get any answer. But in the process of optimizing the algorithm to run on a quantum computer, they optimized a classical algorithm, which is quantum-inspired in its architecture, which was 20% more efficient than the standard algorithms that we've used so far. So again, computer scientists begin to look at quantum computers from a different perspective, much more pragmatic, if you like, less fundamental. But again, this might be the key to solve problems which are very strong physical interest, like problems like quantum chemistry. You're interested in something like optimizing, looking at the ground state of a molecule. Not everything is run on a quantum computer, just a routine, but this might be enough to help a lot. And according to, what about your first question, whether non-cloning theorem is linked with problems like the second principle of thermodynamics? Okay, I don't know, but it's a very interesting question, which is worth looking at, definitely.
So now that you are all smelling the croissants, I think it's time for the first coffee break. I'm sure we're going to have a good week, given that the eigenstate thermalization hypothesis was mentioned in the first session, like the basics joint track session. Thank you, Prof. Palma, for the introductory session, and yeah, thank you guys.